Hello and welcome to this presentation, Machine Vision versus Embedded Vision, Moving Closer Together. I'm John, I'm a product manager at Allied Vision in Germany, and I will guide you through this presentation today. Let's get started. First, some words about Allied Vision. We have been building machine vision and industrial cameras for more than 30 years. We have roughly 300 employees. Our headquarters are in Germany. Our expertise lies in hardware and embedded and host software. We do cameras for the visible spectrum, but also for the infrared spectrum and the shortwave infrared spectrum. We also do custom OEM developments. So the contents of today's presentation, I'll start with some basic things about machine vision system, layout, data generation, requirements. Do the same for embedded vision systems. Before I compare the two systems, then I compare the two cameras, machine vision cameras and embedded vision cameras. Then why I think they are moving closer together, and I'll summarize with an outlook and a conclusion. Here we see a typical, very schematic view of a machine vision system. We have some kind of object on a conveyor belt that needs to be analyzed, some kind of light source, a machine vision camera, a trigger source. The camera is connected via a long cable to a host PC system where the image processing finally takes place. So the object moves on the conveyor belt, gets recognized by the trigger source, which triggers the exposure in the camera. The camera gives a signal to the strobe light to strobe, and the image is then transferred to the host PC system for processing. So that means, again, the trigger source detects the object and generates the trigger. The camera receives the trigger and the exposure inside the camera is triggered. Also, the strobe light gets the signal once the exposure in the camera starts. It is exposing. Afterwards, the image is transmitted to the host PC, and the host PC processes the image and generates the decision for a process control system or any other type of action. Let's have a look at some requirements of a machine vision system. On the right-hand side, we see an example of an inspection line for screws, screw heads and screw nuts for the automotive industry. Every screw is inspected and the screw thread is graded in terms of imperfections. And if a certain threshold is reached, then the screw is marked as defective and it is discarded. So in this way, the automotive industry makes sure that there are no defective screws in a car, which can be, of course, a safety concern. So the first requirement I would like to highlight is that it's important to have a precise input-output control for the cameras which are used. As an input, I can have some kind of trigger source, a light barrier or the like. As an output, outputs are usually used for lighting control, and to be able to control this precisely through the camera is one requirement. Another one is, as I often have various cameras in a system, as also in this example on the right, it's important to be able to synchronize the cameras. And as those cameras are often used in production lines, and production lines must not be down, it's very important that the cameras are as reliable as possible. It's really a worst case scenario if the whole production line is down just because of some camera. So we make sure that this does not happen. As a fourth point, when building a production line, it's very important for the builder that the cameras are easily integrated. That goes for the mechanical side. So there are usually various screw holes, So the cameras can be mounted in various directions, whatever is needed inside the production line. But also on the software side, of course, that the SDK works with various operating system. It works together with various image processing software, so that really a production line can be built quickly and easily, and as little work as possible is necessary. As a last point, of course, also the imaging software which is used for the image processing is very important for the decision making. That's usually then the front end to the user. So that's another crucial point, crucial requirement of a system. Okay, let's now move on to a typical embedded vision system. So here we see a typical schematic, very schematic embedded vision system. We also have some kind of object. It's often moving constantly. We often have a constant light source. For example, in an outdoor scenario, we have the sun, which is more or less constant, but also in an indoor scenario, we just have a constant lighting of the scene. We have a small system, so a very small camera module is used with a usually short cable connected to an embedded board. Oftentimes those are battery-powered devices. They are in one small enclosure. So the decision is generated within this device, and then this transmitted, for example, through Wi-Fi or any other mean, but not the whole image is transmitted, but only the decision or the outcome of the image processing. So what are the steps? So the constant light source illuminates the object. The camera module streams data continuously. So it doesn't just get triggered, but it streams images continuously to the board. The embedded board processes this image data also on a continuous basis, and then the decision is transmitted. Let's now have a look at the requirements of an embedded vision system. On the right-hand side, we see a cash machine or ATM. They usually have cameras embedded, and there an image is generated on a continuous basis, and the image processing which is done is only based on a simple face recognition. So the machine recognizes if there is a face or not, if somebody is standing in front of it or not, and it's keeping records of people who are in front of the machine, so that later on, if anything happened, the image can be found and it can be checked who has taken the money. So as those machines are often small and out in the world, it's important to have a small size, low weight and low power. So we usually call this a low swap factor. Image quality just has to be good enough. Not a perfect image is often necessary. And the image processing is not as sophisticated as in machine vision system. So as I mentioned in this example, it just recognized whether there is a face or not. But of course, also this is getting more and more sophisticated as the power increases. But I mean, in the end, it all comes down, whether you need a machine vision system or an embedded vision system, what does your application really require? And there is not a clear-cut line between the two systems, but there's a big gradient. So there is mixtures of a machine and embedded vision system. And yeah, as the title of this presentation says, I think they are moving closer and closer together by the day. Let's now compare the two systems. So we have a machine vision system on the left and an embedded vision system on the right. If we start with the machine vision system, in terms of hardware, machine vision systems are mostly based on standard components. That goes for the PC system, which is used. Often a server class PC is used, and the cabling is also based on standard Ethernet cables. In terms of software, mostly standard drivers are used, for example, a gigabit Ethernet driver, and also for the image processing, some standard software is used that makes the system quite easy to set up. The processing power which is available if a server class PC system is used is quite high, but so is also the power consumption, usually above 100 watts. The size is not as critical because, as I've shown before, the camera is separated from the PC system. So the overall system size for the PC is not as important because it's away from the production line. On the cost side, because it's based on standard components, the setup costs and the setup speed is quite low. So the system can be put together quite quickly, quite easily. There is not so much customization necessary, so the setup costs are rather low. But then the costs of the system, because it's just standard components, are then rather high. On the other side, an embedded vision system. The hardware often uses many custom components. So maybe a standard embedded module is used, but then oftentimes a custom carrier board is used. Also on the software side, there is much more customization. So it's often based on custom drivers and custom software. So everything is really optimized for this system. And because those are small systems, the processing power is also not as high as if a PC system is used. And also because of the small size, it's important to also have quite a low power consumption. Those are very efficient systems, so they use usually less than 20 watts of power. In terms of size, I already mentioned it. Space is critical because the camera is usually close to the processing, to the embedded board. It's all in close vicinity. So the overall system is small and space is critical. On the cost side, because a lot of custom components are used, the setup cost and to get the system up and running requires a lot of customization. That means a high effort at the start, but because it's very optimized later on, the recurring system costs are rather low, because that's really what it's optimized for, to have low recurring costs, low BOM costs, but then the initial costs are there. So if we now compare the two cameras, starting with a machine vision cameras, what are some pros and cons of a machine vision camera? So they are currently based on FPGA technology. So they have some good image processing capabilities. And with the GenICam standard, we have a very standardized camera control. With UKIVA or USB-free vision, we have very standardized camera interfaces, and we have really a lot of different triggering options for many different applications. But those cameras, they are rather power hungry. FPGA technology is not the most efficient technology. There is no post-processing, so there's only the pre-processing of the image. And generally, machine vision cameras can be rather expensive. If we look at a typical embedded vision module, They're usually based just on the sensor and then some electronics. They are small, they are inexpensive, but there is no pre-processing capability, so pretty much the raw sensor image is transmitted. Therefore, the image quality right from the module is not that good. Often a dedicated driver is needed to be able to control the sensor, and currently there are still no standards for those modules. We've now seen the two systems and also the two cameras and compared them. And so why are they moving closer together? They seem to be quite different. What's the reason? I believe there are two main drivers for this development. One is processing power, and the development of it follows Moore's law, which means it is increasing at an exponential rate, making more and more processing power available in ever decreasing footprint. The other is costs. The costs for electronic equipment has decreased significantly over time and will continue to decrease. In terms of processing power, we can say that the capabilities of new processors are increasing constantly. We see a new generation coming to market pretty much every year. And that means that nowadays embedded boards can really have the performance of workstations of just a few years ago. You can have so much processing power available in a very small footprint, and that opens up a lot of possibilities. And the third reason is there are more and more advanced processing is really possible in small footprints. That means there are more and more dedicated processors for certain tasks. One example is the TPU, which Google released, which is a tensor processing unit. It's really optimized to process deep learning networks. The second driver is costs. We are used to get more and more bang for the buck. And nowadays, system on modules can start below 100 euro. And I think another supporting factor there is really the Linux operating system, which is royalty free. So there are not many licensing costs involved in deploying such a system, or no licensing costs at all sometimes. So these are really the drivers why I think also machine vision systems will move closer to embedded vision systems in the future. Where will this lead to? It is clear that computers will continue to get smaller and more powerful also in the future. Also in terms of camera modules, I think they will get more and more dedicated image enhancement features already integrated on the modules themselves. And the whole processing will move onto the machines. We have a current buzzword, which is edge computing, which really means that the data is processed where it is generated. And we'll also see that the operating system or the whole systems will be more tailored to the needs of the actual application. That means more customization, more dedicated hardware for dedicated tasks. So on the camera side, I think we have a very good combination of the two worlds already. I'd like to introduce you to the Alvium platform. It really has an industrial grade design, but is also kind of a single board module. It's available in various housing and mounting options, so it's very flexible, but also very industrial grade. And it is based around the Alvium technology and an ASIC, which we developed ourselves, which features an image processing library. So it has certain image pre-processing functionality already integrated on the module. It also integrates an intelligent power management, only drawing power when you need it, an overall low power consumption. And it's available with a MIPI CSI2 interface, but also with a USB 3 interface. It supports image sensors up to 1.1 inch, quite large sensors, with up to 20 megapixels resolution. And it also supports various sensors interfaces, so we're not limited to just one sensor manufacturer, but many can be supported in the Alvium platform. To conclude, I believe there are still some challenges for embedded vision to become successful. One is in the often custom hardware design that is used. I think that can be solved by using more standard form factors and also standard camera housings. There are certain standards already available from some embedded module manufacturers, and also on the camera housing, the Sugar Cube format has had a tremendous success in the past. Another challenge is for sure driver integration, especially in terms of CSI2. I think we need more standard drivers which are not dependent on the image sensor that is used. Another challenge is working in a Linux environment and using a custom operating system. I think customers can be helped a lot by providing extensive documentation and support. And then, of course, security and updating the system is always a concern, and that can be alleviated by mainlining the drivers as much as possible. From the camera side, we are trying to pursue all those solutions, and yeah, would be happy to talk to you, and please let me have your questions, and I'm happy to get back to you. Thanks a lot for watching.